We understood about nuclear size and nuclear density, correct? But think about it, you cannot weigh a proton or a neutron, correct? I mean, mass of a proton, mass of a neutron is a very abstract thing to even imagine. Can you take one proton, put it on a weighing scale and say, oh, good, this is the mass? No, not possible, correct? You need to think about a different types of unit itself to measure what is the mass of a nucleon. So this is where the concept of AMU, atomic mass unit, comes into play. Okay, so atomic mass unit, this is that mass which is equal to the mass of 1/12 the mass of carbon 12 isotope. Okay, a very complicated way of understanding. Let me break it down for you. It's a very simple thing. See, 1/12 the mass of carbon 12 isotope. Now, why specifically carbon 12? Because one, the most important reason is that it's a very stable element. Okay, it does not disintegrate very easily. So, carbon 12 isotope has a very stable mass. And because of this, we take carbon 12 isotope. So, carbon 12 isotope has 6 protons and 6 neutrons. Okay, so what do? We take 1/12 the mass of that one. So you will get the mass of one nucleon, which is basically mass of one proton or one neutron. That's why we say 1 AMU is the mass of that particle, which is 1/12 the mass of carbon 12 isotope. Alright. Now we all know that 1 gram of carbon 12 isotope has Avogadro number of molecules or Avogadro number of atoms. Correct? Avogadro number we all know, 6.023 into 10 to the power of 23. So, mass of one carbon 12 atom will be 12 divided by 6.023 into 10 to the power 23. So, mass of one nucleon or 1 AMU becomes 1 by 12 into 12 by 6.023 into 10 to the power 23, which becomes 1 by 6.023 into 10 to the power 23. So many gram, correct? Which becomes 1.66 into 10 power minus 24 gram. SI unit of mass is kg. So 1 AMU becomes 1.66 into 10 power minus 27 kg. This is what we call as 1 AMU, 1 atomic mass unit. Now when we talk about the mass of a nucleon, like say proton, mass of proton MP is equal to, look at the value, 1.0073 AMU, or we just call it as units U. Okay, 1.0073 U. Mass of a neutron 1.0086 U, and mass of the electron is this, see, 0.00055. Don't you think it's negligible? Negligible compared to the mass of proton and neutron. That's why, remember in the previous videos I told that atomic mass is only the mass of the nucleus and not the mass of electrons. This is the reason. Because even if you have like hundreds, maybe like thousands also, 1000 protons, 1000 neutrons and 1000 electrons, if you have it, of course it doesn't matter. I'm just giving you an example. If this is the case, only the mass of protons and neutrons are considered, because the 1000 electrons makes no difference. Alright, it makes no difference. That's why, so these are the masses of these subatomic particles, protons, neutrons and electrons in terms of unit. Now, you have understood what is the mass. And before this particular video, we understood mass energy equivalence, correct? Now let's try to understand, what if you convert one atom or one AMU, one atomic mass unit, completely into energy. Okay, completely into energy. There is no spare of whatever it is. Okay, remember we are talking about one AMU and not of one complete atom, just one AMU. To understand this one, we need to understand how do we measure the energy in atomic and nuclear level. Alright. Now, whenever we talk about this, we have a concept of electron volt. See, electron volt is what? It is the energy of an electron, okay, energy of an electron when we accelerate it through a potential difference of 1 volt. Alright, so you have 1 volt, you accelerate the electron. Okay, what is the energy gained by the electron? That is basically what we know as electron volt. So since electron volt is energy, 1 electron volt becomes 1.602 into 10 power minus 19 into 1. So you will get 1.602 into 10 power minus 19 joule. This is what we call as 1 electron volt. Fair enough? But it's a very small quantity, right? So generally you will have in terms of mega electron volt or giga electron volt, either of these two. But let's talk about AMU because that's what we are more concerned about. When you talk about AMU, 1 AMU, atomic mass unit, this is where we use the mass energy equivalence. E is equal to mc square. So E is equal to 1.66 into 10 power minus 27 into 3 into 10 to the power of 8 whole square, which becomes 1.49 into 10 to the power of minus 10 joule. Okay, or this becomes, see, when you divide this by the value of 1.6 into 10 power minus 19, you will get approximately 931.25 electron volt. Sorry, 931.25 mega electron volt. So what we can write is that 1 AMU is equal to or approximately equal to 931 mega electron volt. That means, think about it, if you take 1 proton or 1 neutron, that's almost 1 AMU, correct? If you take one of those nucleons and if you completely convert that into energy, you are going to get 931 mega electron volt of energy, which is so much. It is a lot if you compare in the nuclear scale. Like in the sense, suppose if I have to, scale it up to normal level. Okay, suppose let's say you are going to talk about 1 kg of water. Assume that you have 1 kg water. If you completely convert that into energy, you are going to get so much of energy, you can run the whole world for about 10 years. That much of energy you guys are going to get. That is the energy equivalent what I'm talking about. So 1 AMU gives 931 mega electron volt of energy. Okay, so this is with the help of mass energy equivalence. So remember what is 1 AMU and remember the energy equivalent of 1 AMU. So in the next one, you guys are going to understand what is binding energy, what is mass defect, and how we use this concept of mass energy equivalence and understand about stability of the nucleus.